Hello. All right, let's get started. Is there any questions, any questions, any questions? All right, this is your question. If I regenerate, I think the name regenerates too. So this was definitely yours. Okay. I assume you would know how to do this if instead of the product, it said to sum, right? I would start yelling at you if you claim you don't know. This is if I replace the word product to sum, it becomes one of the easiest problems. Let me copy down there's 8, so there is x, and there is 12 less than 4, there is 4x minus 12, right? And there is 216. You would know that if the sum was then x plus 4x minus 12 equals to, well, 216 would be way too much, right? So that would be okay. So what if the product is given? Well, then we multiply. And so what? This is a very benign quadratic equation, right? So you just state it, just don't get, quadratic word problems. The setting of the equation is no harder than setting up the linear equation. And I think that's the part that students are worried about, not solving them. Now, when I gave you this homework, we didn't have the AC method, so this should boil down to something like x squared, not 4x squared. But you see, it will, because you can divide by 4, and then we get x squared. Okay, so then it's x squared minus 3x minus 216 divided by 4 is 54. Oh, right. And then trial and error, and I'm thinking 6 and 9, right? Because 6 and 9 multiply to this, and that they have that difference. So x. It's interesting because, well, it would be interesting if there are two solutions and it happens, not in this case, I believe, because this minus says that one of them will have a plus, and that would mean a negative age. So one of them will be obviously garbage. But sometimes it's an interesting conversation that the equation boiled down to quadratic, we got two solutions, they're both reasonable. Which one is the solution? Sometimes they both work, but sometimes you will have this instinct that there should be only one answer. So if I put 6 here and 9 there, the bigger one should get the 9. The bigger one should get the minus. There it is, right? So -6, which is very easily ruled out. -6 is not a good age, although it's pretty young. And 9. So then we go back and say x is 9, and 4x minus 12 is 24. 4 times 9 is 36. Yeah. And 9 times 24 is 216. So tell me, what was the problem? Setting it up or solving the quadratic? Solving. Okay. Actually, I prefer that. Yeah, it was just right after we did trial and error. So as long, this is my math from my side. So as long as this number is a divisor of that, the whole thing washes out and you just get something that's good for trial and error. But now you also have the AC method, although AC method is not really needed here. Okay. Any other questions besides 53, which I insist on covering? Okie dokie. So I have that ready too. This was number 53, and Pythagorean theorem is so important. I covered it in both 98 and 99. And the 99 handout has this problem worked out. But I wanted you to kind of get a taste of the Pythagorean theorem is not necessarily, yeah, here are two sides of a right triangle, find the third one. Yeah, there are going to be all kinds of other interesting stuff. Okay, so this is in the shape of a semicircle. And I think it was in my other class where we saw examples where the Pythagorean theorem comes up with vengeance, usually with circles, where there is not only no right triangle, a straight line isn't in sight. I'll show you an example. So circles, and this is an example where, there is no right triangle. We have to come up with one. So at the point 6, okay, all right. So this is what we know. We know that if we stand 6 feet, yeah, this is probably a bad picture. I think it's more like that. I think these ratios, this is more like 2 to 3, 6 to 9. So this is what we know. If we stand 6 feet from one end, then the height at that point is 9 feet. And the question is, what is the maximum height? And now that's already kind of premonition of, this is what calculus asks. Instead of, when is it 10? It says, well, consider all possible values and find the maximum. This is called optimization. And it's a very reasonable thing because we model a lot of things with mathematical expressions, and then we look for maximum of profit if we modeled profit with a mathematical graph, or you want to minimize risk. So the smallest, largest value of an expression, that's the next level of abstraction. The first painful change in your math life was when letters came in. Letters came in, and that was a shock to the system and equations, and you got used to it. This is the next one where they say, okay, you don't get an equation. You just get one side, and you have to find the maximum possible value. And this is sort of a glimpse into that. But because this thing is a semicircle, basically, all they're asking is the radius, right? They're asking for the radius, because that would be the greatest height in a semicircle. Okay, so basically, they're asking for the radius, which I'm going to take out because it's not going to help. So there is a right triangle here. However, the right triangle that you really need is this one. It's very common that if you have a point in a circle, you want to connect it to the center. If you use this other triangle, you can find the hypotenuse, but it's not going to give you anything you want. This one, on the other hand, now, how do you find this line? Well, not for the first time. This is a struggle. And you have to, in geometry problems, the solution is easy, and it falls into your lap after you draw in just one magical line. Getting that magical line takes hours of sweating and frustration, and so you're not going to run into it for the first time, but this is sort of how word problems in geometry work themselves out. Well, they don't work themselves out. You have to work them out. So here is the thing. If you call this X, now comes the big deal. Number one was to come up with this triangle. How can we label this side? And don't tell me Y. Don't tell me the letter Y. Tell me in terms of X. Or you can use R. I usually go for X right away, but we can use R. You want? Yes, R minus 6. And then we just did the Pythagorean theorem, which is probably the most commonly stated geometry statement algebraically. R minus, so the hypotenuse is opposite right angle. So R minus 6 squared plus 9 squared equals R squared. I try to go for the A squared plus B squared equals C squared. And what's lovely is that this is going to be linear. After you cancel out, you see r squared will cancel out. You see, we can subtract r squared from both sides. And this does feel like that this should just have one solution, right? Because there is a fixed height. And then, yeah, so I don't know how to explain it, but I think there is a geometric intuition that says there should be just one solution here. I guess maybe I'm wrong, but so then what we have is 12r is whatever 36 plus 81 is. 117. 117 add the digits, divisible by 9. So 117 over 12 is not the final answer. Let's divide by 3. 39 over 4. Or, you know, if the denominator is as nice as 4, we can actually go for it. It's nice. Actually, we're going to talk about these decimals today. So there, it's 39 over 4. So these are even, I think, even tougher than word problems that are stored in language, because you have to get your visual mojo going. But this is something, word problems and these sort of geometry problems and all of these things are just another skill you work at. And you work at it, you get better. There's nothing mysterious about math. It's just another skill set that you're going to get better if you work on it. Okay. Now, any other questions? So last class, we were talking about the difference of cubes theorem, but I put it in a bigger frame, a bigger perspective. Sort of the big picture was that a squared minus b squared can be factored into a pair of conjugates, a minus b times a plus b. And there's something going to happen in Algebra 2, Math 99, when I always go, which is going to be a reason for me always starting with a plus b instead of, but now I'm swapping, because you see a cubed minus b cubed can also be factored. And the first piece is a minus b, and the second piece is a squared plus ab plus b squared. And then a to the fourth minus b to the fourth can also be factored. And guess what? The short little factor is a minus b. And the longer one is, well, basically, you can match the first with the first to get a to the fourth. That would be a cubed. And then all the signs are plus. And for the next term, you just throw away an a, pick up a b. So instead of 3 a's, let's have 2a and a b. And then let's throw away, switch or swap another a for a b. And you're done when all you have is b. But these are always should be 3 letters, degree 3 terms. This is a times a times a. This is a times b. Here, everything is degree 2. Here, everything is degree 3. And a to the 5 minus b to the 5 can be factored, where the shorter piece is, surprise, surprise, a minus b. It's basically copying the other side without the exponents. And then you just match the first piece against the first piece, and then all the signs are plus, and then you, for each new term, you throw away an a, pick up a b. Right, and so on. So a to the n minus b to the n can be factored, and the first piece is a minus b. And this has this has tremendous applications on number theory, on divisibility things. For example, let me just finish this and I'll show you stuff. A to the n minus 1 plus a to the n minus 2 times b plus a to the n minus 3 times b squared, all of a until all we have is b. Okay, so this has applications to divisibility. suppose we want to look at something ugly like 7 to the 6 minus 1. Now, if we think about 7 to the 6 minus 1 as 7 to the 6 minus 1 to the 6, because 1 is just very versatile that way, that's going to be 7 minus 1 times other stuff. So it's divisible by 7, divisible by 6, right? So 7 to the 6 minus 1 is divisible by 6. Well, we can get that in other ways. That's not so earth-shattering, but actually, let me take it up a notch. Let's do 7 to the 100 minus 1, which is 7 to the 100 minus 1 to the 100 is divisible by 6, clearly. But 7 to the 100, well, what if I told you that 7 to the 100 minus 1 is also divisible by 48? Why would that be? Because we can look at 7 to the 100th power as 7 squared to the 50th power, which is 49 to the 50th power. And then 7 to the 100 minus 1 is the same as 49 to the 50th power minus 1 to, at this time, 1 is kind of cool that way. And that's divisible by 48. And so whenever the exponent is a divisor of 100, what's 7 to the 4th power? 7 to the 4th power, that's going to be pretty big. Is 2401. So here is the statement. 7 to the 100 minus 1 is divisible by 2400. Am I correct there? Yeah, because 7 to the 100 minus 1 is 7 to the 7 to the 4 to the 25, which is 2401 to the 25th power minus 1. Oops. And that's 2401 to the 25 minus 1 to the 25 is divisible by 2401 minus 1, which is 2400. So if someone asks, oh, the last few digits of 7 to the 100th power minus 1, it's not just the last digit, but the last few digits. There are all kinds of divisibility consequences of this lovely factoring technique, and it's very universal. Now, I showed you this whole thing, but really, what is core material in 98 is the difference of cubes theorem. And I forgot to mention, but it is important that whenever you do the difference of cubes theorem, you get this short piece and this long piece. But this long piece cannot be broken down any further. So you don't have to worry, oh, maybe this can be further factored. It can never be. It can not be factored. I kind of avoided it, but there are plenty of stuff that this cannot be factored, sort of like a prime number. The reason I didn't give you a lot of those, because what is the criteria for something cannot be factored? In this class, the criteria is, well, I tried for 2 hours and I couldn't find it. That's not acceptable, because a paranoid person would say, and if you just stayed 1 more minute, maybe you would have found it. And so in this course, we don't have a sort of a bulletproof justification that this thing, no matter how hard you try, is not going to factor. In the next class, we will have one. We will have sort of a mathematical proof that this thing can never be factored. Okay. But just remember that whenever you use the difference of cubes theorem, you don't have to worry about the long piece. It cannot be factored further. All right, so this is what we did last class. Now I want to do the sum of cubes. But the sum of cubes is, well, the whole thing is interesting. Here, basically, you have seen these worked out. And this is sort of how the idea of conjugacy gets generalized. What is the idea of it conjugates multiplying? Well, we're going to have the same things, but the opposing sides. So there is going to be cancellation. And if you look at here, if you multiply a by ab squared, you get a squared b squared. Well, we get minus that if you multiply these two. Minus b times a squared b squared. Those two will cancel out. So this is just a sort of a generalization of the idea of conjugates. But the conjugacy is always in the short piece. Now, there is another version of that that only works for odd numbers, which is interesting and important. So a plus b is a plus b. A squared plus b squared cannot be factored. When we cover the difference of squares theorem, hopefully I made a big fuss about it, that the difference of squares theorem, that the difference of two squares can never be factored. But the sum of cubes can. And there are two pieces. The first piece is kind of, you remember what I said with the difference? I said the short piece is coping the other side without the exponent. That's exactly what happens here. Is a plus b. And then the other piece is going to be generated the same way. So you have a squared, ab, and b squared. But now every second sign is plus, minus, because the conjugacy is in this longer piece. So it's going to be a squared minus ab plus b squared. And that's what's called the sum of cubes theorem. Now, a to the fourth, we'll work it out. You will see how, but I just want to show you how to generate this. A to the fourth plus b to the fourth cannot be factored. But a to the 5 plus b to the 5 can. And the shorter piece is a plus b. And the longer piece is, now the pieces are no surprise. We're going to match the first with the first. So that's a to the 4. And then the next term is going to be throw away an a, pick up a b. The only difference is that we start with a plus, then the next is minus, then plus, minus, plus, minus. So this was a plus. So minus, we throw away an a, pick up a b. Now plus, throw away an a, pick up a b. Now minus, throw away an a, pick up a b. It's magically just going to work. We'll multiply this out, but a to the 6 plus b to the 6 cannot be factored. Whenever that exponent is even, there's no factoring. However, a to the 7 plus b to the 7 can be factored. The short piece is copying the other side without the exponents. And the longer piece is going to be, as before, it's just now the conjugacy is in the second long piece. So you match a to the 6 times a is going to be a to the 7. And then this was a plus, so we go minus a to the 5. B is not going to, no way I'm going to fit there. Plus a to the 4 b squared minus a cubed b cubed plus a squared b to the 4th, almost, minus ab5 plus b to the 6th, and so on. I think you can generate it now. Now, the one that you're responsible for, the way I memorize them is basically the cubes, the sum and difference of cubes. So the way I memorized is a cubed plus b cubed and a cubed minus b cubed. They both have the same creatures. A, b, a squared, a, b, b squared. And then two more pieces of information. Each formula on this part has exactly one negative sign, and the shorter part copies the other side. So the shorter piece is the other side without the exponent. So this is a minus, this is a plus. And both formulas have exactly one negative sign. So this one is done. And that one negative sign is sort of in the middle. So work on being able to recall this because they're quite important. Lately, you know, math teachers write the textbooks and they don't want to they don't want to take extra time reteaching these theorems in college algebra and calculus. So they started to take out problems from these books that boil down to a difference in sum of cubes, but that's completely artificial, weakening down the material. This comes up quite a lot. If we didn't do this, let's just make it easier. The textbooks that come out every year, they are weaker than before. So if you can get your hand on some old textbooks, like 60s, 70s, those are much better than the ones that are out now. They are much better books. Okay. So these are the theorems, and now I'm going to show you why they work. So we're going to multiply these stuff out. So let's look at a plus b times a squared minus ab plus b squared. It's going to be the same idea that this here, this pair, when a meets this minus ab is going to be, that's a minus a squared b, is going to be canceled out by this plus a squared b when these two meet. So we can expect 6 little pieces. First, we're going to multiply everybody here by a and then by b. Oh, the signs, this is easier than, there's no minus to worry about here. So when we hit it with a, we get a cubed minus a squared b plus ab squared. And then when we hit it with b, we get plus a squared b. You see that? There is the cancellation, minus ab squared plus b cubed. Cancel, cancel. There it is. Let's see, a plus b to the 5th power, a to the 4 minus a cubed b plus a squared b squared minus ab cubed plus b to the 4. Okay, so you know what's in between is a to the 4th plus b to the 4th cannot be factored. So no matter how you try, and you should try a few, it's never going to work out. I'm not going to do that, but you can try to figure out this pattern, apply it when the exponent is 4, and it's just not going to work. First of all, this last piece will have a minus, right? You'll play around with it. So now when we multiply this out, just so you know, we're going to get a to the 5 plus b to the 5. We're going to have 10 little pieces. First, when we multiply everybody from here by a and then by b. So it's going to be a to the 5 minus a to the 4b plus a cubed b squared minus a squared b cubed plus ab4. So we just hit everybody here by a. And then now we're going to hit everybody by b, but I'm going to do that usual trick. But I don't continue, I go new line and tab. So I'm going to start here. There is a plus a to the 4th b right there, cancellation, minus a cubed b squared plus a squared b cubed. It's almost like magical, but it just works. Minus a b to the 4th plus b to the 5th power. And then these things all cancel. These are called special products because they're so special. Okay. Any questions? So don't try to cross out x. You can only knock out things in a fraction from products. You can only knock out factors. You cannot subtract the same number from both numerator and denominator. So it would be pretty bad. It's pretty offensive too when you start crossing out. Just factor it. And the top is going to factor by the sum of cubes theorem, and then x plus 1 will cancel out. It's pretty easy when it's x and 1. This is the simplest one probably. Oops, over x plus 1. My bad. And then we cancel out and we get x squared minus x plus 1. And if you're not sure at first, you should just multiply it out, because just to make sure that we factored correctly. So we're going to hit everybody by x and then everybody by 1. So x cubed minus x squared plus x squared minus x plus 1. So it's x cubed plus 1. So this is quite important. X cubed plus 1 over x plus 1 is x squared minus x plus 1. That's quite interesting. Okay, let's do another one. Okay, so you have to figure out, okay, this is not going to be the difference of anything. This is going to be a sum. And the squares don't have a theorem. You cannot factor the sum of squares. So this has to be a sum of cubes. And then you should recognize what are we cubing? 5 cubed is 125. And 2b squared, right? And the exponents behave differently, right? We take the third root of 2. We're not taking the third root of 6. We're just dividing it by 3. And so if I state x cubed minus y cubed is, plus x plus y times x squared. What does this always happen? X squared minus xy plus y squared. Basically, x is going to be played by 5a, and y is going to be played by 2b squared, right? 5a is cubed. 5a plays the role of x. 2b squared plays the role of y. And so the most common mistake is we have 5a plus 2b squared times 5a squared minus 5a times 2b squared plus 2b squared squared. And so this is wrong. The error is we have to square the whole thing, right? It probably, it's not that hard there because of the exponentiation, but there's no exponent on 5a, so you might be tempted to forget that parenthesis. But what we're squaring is 5a, not a. So we have 5a plus 2b squared times 25a squared minus 10ab squared plus 4b to the 4th power. And that's the final answer. Any questions? Okay, so that was the last factoring technique over the integers. So we have the GCF for everything. The GCF is sort of the first step in every factoring technique. And then if it has 2 terms, now we know 3 of them. There is the difference of squares, the difference of cubes, and sum of cubes, but they all have just two terms. But you know there is a bigger picture, that if it was a to the 10 plus b to the 10, that can be factored as well. If it has three terms, that's the most common, a general quadratic, something like ax squared plus bx plus c. Then you can do the trial and error. If the multiplier of a, the coefficient of a, is 1. And otherwise, the AC method and if there are 4 terms, grouping is the way. So sometimes people find that it's hard to decide what factoring technique to use. Actually, it's not that difficult. Just count the pieces. And there are specifically different techniques depending on the number of terms. This is some, yeah, you know what the two-term expression looks like. So that's it for factoring. It's not that bad. And that means you can factor pretty much whatever comes your way, as long as numbers are nice. That means everything quadratic and some of the degree 3 things. Not all of the degree 3 things. If you have something like x cubed plus 1, you can factor that, but x squared plus x cubed plus 5x squared plus 1 is not that. It's not two terms, right? So, but quadratic, pretty much everything. The AC method covers everything. Okay, any questions about that? All right, so remember last class I told you about the flea that sits on the number line? Did you think about it? Let me try to find it. I'm pretty sure I asked you last class. Yes, I don't want to write down the whole thing again. So here is the student view of our class. And the last class was here. So I'm going to click on this class notes. And here it is. It starts here. So a flea is sitting on 0, then it jumps to 1 using 1 jump, then jumps back to 0 using 2 equal jumps, and then jumps back to 1 using 3 equal jumps, and then back to 0. My spelling is atrocious. Wow, Jesus, that's bad. So I don't want to write that down again, but basically here's what happens. The first round, the flea starts at 0 and lands on 1. Which, there it is. The second round, it starts at 1 and it's gonna take 2 equal jumps to go back. So it's gonna start at 1 and then a half and then 0. But I'm just gonna turn them around and say 0, half, 1. The third round is gonna be 0, 1/3, 2/3, 1, right? Because it's gonna use 3 steps. First round here, second round. So the third step is 1/3, 2/3, 1, because it makes 3 equal jumps to go to the other number. Fourth round, it's gonna land on 0, 1/4, 2/4, 3/4, and then 1. And the question, and it goes on, and this display is jumping as we speak. Imagine that 2000th round, it's gonna just have a tiny jump, 1/2000, and so it's gonna have to jump a lot to get to the point, but it does it. And so the question was, does this flea land on every point on 0, 1 eventually? And this is something that I don't think you I just thought you should guess. You don't have to do anything more than just guess. What do you think? Just guess, it's okay. There's one brave answer, yes. So first of all, how do we think about this thing every point? Because we cannot just imagine that let's videotape this please motion and let's follow, because then we're going to be following this thing forever. So that's not how we do that. How do we approach this thing every point? And so here is my recommendation: fix a point, a really nasty, ugly point, and ask yourself, will this flea eventually land on that? And so instead of thinking every, let's pick one and see if the flea lands on it. Or what kind of number? So you want to focus on one fixed number. And so if you want to make it really nasty, you could say, well, by the way, the rest of you are cowards. No one is laughing and pointing and mocking people, and you wouldn't even guess a yes or a no for me. That's not very brave of you. So let X be 13/41. Will the flea land on this? The answer is yeah. On the 41st round, it's going to jump. But I don't know whether it starts from 0 and goes to 1 or vice versa. But if it starts at 0, then on the 13th step, so in the 41st round, it will land at the 13th. Or what's 41 minus 13? That's 40 minus 12. That's or 28th step. Depending on whether it's coming from 0 or 1, but it's going to land on it, right? And now, can you think of any number on which it wouldn't land? And by the way, you can notice other things, like it's not only it's going to land on something like half, it's going to land on half infinitely many times, right? It will land on 1/2 infinitely many times, because 1/2, 2/4, 3/6, 4/8, 5/10. These are all different ways we can write 1/2. This is in when it jumps 2 equal jumps in the second round. But when it jumps 4 equal rounds after the second step, it will be there. Or in the 6th round, the 3rd step is going to be there. So it will land on even this one infinitely many times. The next time is when it uses 82 jumps, and the 26 or 56 step is going to land it on this point. So not only it lands every point, actually it lands on every point infinitely times. Well, actually no. So when I was a student, my answer was yes, but the correct answer is no. There will be points that this flea will never touch, even though it can go infinitely long, it will never reach certain points. In fact, there are more points that it will miss than the points that it will hit. And that's quite a shock to the system. So actually, yes, there will be lots of points that it will miss. Actually, there is infinitely many numbers that it will miss, infinitely many that it will hit, and infinitely large sets are hard to compare, but there is a way to compare them, and then the points missed are much bigger than the points hit. That's the second shock. So let's set aside and we will return here. Thank you for the one person who bothered to talk to me on this one. So we're going to come back. What we're going to do now is related, but you're not going to see the connection for a while. We started with the set of all natural numbers, right? And if we started to do operations on it very soon, we realized we need other numbers if we want to subtract and divide. Subtraction was fixed by throwing in the negative numbers and 0. So these are the integers. And now the integers, if you grab 2 integers, you can add them, multiply them, and subtract them, and the result will always be an integer. But division is still not fixed. So we throw in something that you know as fractions. But now I'm going to be a little bit more specific and say fractions of integers. And let me throw in a definition. A number is rational if it can be written as a quotient of 2 integers. And you can think of fraction, but I'm using the word quotient because then you understand why the set theory symbol of rational numbers is Q. It's after for quotients. It's a quotient set for take 2 integers, and if the second one is not 0, then divide. Division by 0 cannot be fixed. Okay. So you can think of the rational numbers as the integers and the fractions together. And basically, this is what it looks like. Subsets. I can tell you the word subset and you understand. So, and it's not only that we preserve the set, but we try to preserve the math we already have. So here are the natural numbers. And there are all kinds of important truth facts about them, like 2 plus 5 and 5 plus 2 are the same and stuff like that. And we were very careful to preserve those statements when we enlarge this system by throwing in new numbers like -1, -2, 0. And then, so it looks like that this is a set, the rational numbers is a set containing everything before, but that's not the justification. We should see why we could say that 10 is a rational number, which I'm gonna, you see this is a lot of writing, so I'm gonna use notation y. 10 is an element of the set of all rational numbers. This is how we really quickly say it's a rational number. Now, the definition is a number is rational if it can be written as a quotient of two integers. Well, 20 over 2. You do not have to find the reduced one. 10 is the reduced form, actually. But if you can find, and I think the easiest is 10 over 1, right? If you can find, and this is the proof why every integer is automatically rational. Every integer, if n is an integer, then n over 1 equals n is rational. So we can say that the set of all integers is a subset of the set of all rational numbers. That is a little bit, I was kind of sparing you the heavy notation until now, but you can cut down on the writing a great deal using these notations. So if n is an integer, then n is n over 1, integer, and therefore n is also rational. So every integer is automatically a rational number, which means we can draw them. We can draw the set of all integers inside the rational sets. So what is true about this flea, that it will hit every rational number between 0 and 1. And so if you think yes, and by the way, when I was asked this question, I had the incorrect answer yes, because I too thought that the rational numbers fill up the number line, but that's not true. The rational numbers don't fill up the number line. There are numbers. So what's the next step? The next step is real numbers. So there is natural, integer, rational, real. And someone worked real hard, pun intended, to prove that the real numbers, there is exactly as many of them as points on a line, hence the number line. The real numbers fill up the number line in a perfect way. Every point corresponds to exactly one number, and there is a point for every number. So it's a one-to-one match. The real numbers fill up the number line, not the rational numbers. So there are some weird numbers that are real numbers, and they make the difference. So what kind of a number could be a real number that's not rational? What kind of a number could that be? Okay, so a number is irrational if it is not rational. That means you take down this definition, but you just have to strategically place the word not in there. So a number is irrational if it cannot be written as a quotient of two integers. And together, the rationals and the irrationals fill up the number line. And I told you in a way that there are more irrational numbers than rational numbers. When I told you that the flea will miss more than it will hit. So those are irrational numbers. I'm pretty sure. Can you just recall from your vague past, from those memories, traumatic memories you blocked out? Do you remember any number that you were given as an example for an irrational number? I'm expecting 2. Examples for irrational numbers. Either type that in or just type in that you're here, because I'm not sure. Just type in into the chat box that you're still sitting in front of the computer. Or, okay, or what you think might be an irrational number. It's okay to be wrong. 0 is 0 divided by 1. And so you see visually 0 is a rational number, but again, thank you for trying at least. 0 is rational, 0 over 1. The problem is when you try to put 0 in the denominator. But keep at it. That's it. Only 2 people are in front of the computer. Jesus. That's not very nice. Only 2 people. All right. That's. Well, at least you guys learned how to sign in. Some of my advanced college level class couldn't even learn that. Okay. All right. So it's the 3 of us then. So square root of 2 would be an example, and pi. Those are 2 famous examples. So famous irrational numbers. Square root of 2 and pi. They both come to us from geometry. And you could think about, okay, now if you take the rational numbers are, you can perform any of the 4 basic operations without needing any other number. Okay, division by 0, but that cannot be fixed. You can add 2 rational numbers, and the answer is always rational. If you think of 10 as 10 over 1, then rational numbers are what we think of fractions. And the sum of 2 fractions is always a fraction, or better. And the difference of 2 fractions, product, quotient, so you can do anything. So you could say, why did we need to go out to this at all? And that's a good question, because these reasons were sort of reasonable and algebraic. Here, we fixed subtraction. Not all subtractions can be performed inside of the natural numbers. 5 minus 2, yeah, but 2 minus 5, we had to develop something we call -3, right? 2 minus 5, not a natural number. And this step out when we fix division. So there is no basic operation to be fixed. So why were mathematicians so greedy that they had to go and step out into an even bigger number set? And the reason for that was not quite algebraic. Here is the reason. The kind of numbers we have been studying are, this is 1, this is 2, this is 3, this is 4. These are natural numbers, like they're physically out there. You can look at it as part of physics. There is something physically true about them, and then we can start having operations, subtraction, addition, multiplication, and we can develop the rational numbers. Even square root of 2, we can say, I'm thinking of a number that if you square it's 2. So we can sort of get there. But pi is where is pi coming from? Do you remember what you were studying when pi first come into our life? So what were we studying when we first met pi, one of the most famous irrational number, I think? Well, check this out. If you take the square with sides 1 and 1, and you want to know how long the diagonal is, well, the Greeks needed to know that, the ancient Greeks, for architectural purposes. you know, to make a building a little bit more stable, you probably want to connect this. I don't know what but it's reasonable that you want to know what is the hypotenuse of the isosceles right triangle with sides 1 and 1. And the answer is, if we call this x, 1 squared plus 1 squared equals x squared. So x squared equals 2. And you can do some funny stuff. You can get close with the calculator, like, okay, 1 squared is not enough, and 2 squared is clearly too much. What about 1.5? If I square 1.5, it's more than 2, right? So 1.5 squared is 2.25. So if there is a number that squares to 2, it's going to be less than 1.5. I should have put it there. 1.4 squared, on the other hand, is not good enough, right? 1.4 squared is 1.96. So if there is a number that squares to 2, it's between these two numbers. Well, how about the one right in the average, right in between, is 1.45. If we square this, now it's too much, 1.45, but it's getting closer, right? 1.45 squared is 2.1025. But there is not an easy way, or using fractions, there is not an easy way to actually bump into something. You can get extremely close. 1.41 is pretty damn close, right? 1.414, and you can just trial and error your way in it, like down if it's too much, up if it's too small. But we're looking for a number that is exactly 2 when squared. And that number came to us from geometry, actually. And so did pi. If you take a circle with radius 1, then as it turns out, the circumference is 2 times this weird number pi, 6, well, pi. Pi is so important. There is a button in your calculator. That's pi right there. Pi is, by the way, the Greek version of the letter P. You see pi, and then you click equal, is 3.1415. It's, if you take a unit circle, which is a circle with radius 1, the circumference is 6 and 2/8. The circumference is twice this number, 6.283, and the area is that number. So, you know, saying that this is 1 and this is 2 and this is 3 is is very different from someone saying, I want to put numbers on distances. If I want to call this 1, then this distance. Then, yeah, this distance is 2, and this one is 3. But if you make a square with size that, then this length is square root of 2. We did not need, so square root of 2 is not something, well, I'm getting ahead of myself, but square root of 2 is an irrational number. Today, we're going to prove that, hopefully. We might run out of time, but that's a big, 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 big deal. Square root of 2 is irrational, which means that you cannot take integers and the 4 basic operations, additions, and work your way towards square root of 2. You cannot take square root of 2. So this is these two ways of thinking of 1, this distinct counting things or putting numbers on distances. Those are 2 different things. And I already told you the real numbers, points on a line. So the minute we wanted to put distances on lines, that forced us out from we added the rational numbers, and that gave us the real numbers. And if I want to do this picture, here is the natural numbers, here is the integers, here is the rational numbers. You see what I'm trying to say with the sizes here? This here is the irrational numbers. There is not a notation for them. And this is the real numbers. There is more irrational number than rational one, much, much more. I remember the shock to my system because I found irrational numbers to be outrageous. How come you cannot find two of them so that you divide and that fraction will square to 2? There are so many integers to choose from. You can go up to billions and billions and billions, and yet you're not going to get there. So I remember I was outraged. That's a terrible. I found that somehow it was a moment of disillusionment in mathematics, that there are such heinous numbers, such as square root of 2, so you cannot write down as a fraction. It's like, how are you going to write it down? And after some conversation, this is the way we're going to write it down. So algebra 2 is going to be full of, okay, how do we manipulate numbers if our number system invites these hideous radical expressions like square root of 2? We're going to have to go back to FOIL and all that stuff and revisit it, because there is no other decent way of representing these irrational numbers than square root of 2 or pi. And then the second outrage is not only these heinous numbers should exist, but there is more of them than the nice ones. That's terrible. So now I'm going to prove to you, maybe not today, but Wednesday, we're going to prove that square root of 2 is irrational. But first, let's just look at rational numbers a little bit. Oh, before I move on, is there any questions of the two of you who are actually in front of the TV or computer? These other four, you better not come to me for letters of recommendation or stuff like that. All right. Where is it's gone again? So what I want to say first is that if you're given a number, it's either rational or irrational. You cannot change its nature. But given whether it's rational or irrational, it's going to be much harder to prove it or much easier to prove it. So given a number, given a real number, it is rational or irrational. This fact cannot be changed. But it's much easier to prove that the number is rational than to prove that it's irrational. All right. So remember, a rational number is one where we can rewrite it as a fraction of two integers. So tell me, why would 3.5 be rational? Prove it to me that 3.5 is rational. So the way we prove it, instead of resorting to physical violence to persuade or yell, we just produce two integers such that if we divide, the result is 3.5. So can you rewrite this can you convert it into a fraction of integers? Prove that 3.5 is exactly rational. Now, it's 7/2. And famous numbers you can recognize, but I want to show you kind of a more general thing. How about 3.21? That doesn't look so nice. But we can say, I think this is rational, and we might be right or wrong. Actually, this is a rational number, which is why it's going to be possible to prove that it is rational. So to prove that it's rational, we have to write it as a fraction of two integers. Well, let's break down the project. Let's just write it as a fraction first. And now let's work on the fact that they are not all integers. So what is the thing we can do to a fraction? We can multiply upstairs and downstairs by the same number. And to fix a decimal, we have to multiply it by 10 powers. So for example, 3.21. You see, mentally, if you want to move the decimal point at the end, you have to move the decimal point 2 decimal places. That means 2 zeros. So if you multiply by 100, there it is. So if you multiply the top by 100, that will fix the top. And we are now committed to 100 because it has to be the same number upstairs and downstairs. So there. So now I think you understand that we kind of proved that if a decimal ends, it's called a terminating decimal. So let me just write down this statement. In fact, every terminating decimal represents a rational number. Because if we have something hideous like 98.2023, what's today? 5-1. Well, terminating means there is a last digit. It doesn't go on forever, like 1/3 goes on forever, right? 1/3 goes on forever, ever. But if it has a last digit, then we can grow a 1 and a suitable 10 power will fix the top. Now we're going to need 1. So how many digits are we going to cross? 1, 2, 3, 4, 5, 6. So we need a cool million upstairs and downstairs. 6 zeros. There is something very nice about 3 zeros is 10 to the 3rd power. 4 zeros, there is usually a mismatch, like misalignment by one up or one down. This is perfect. And that will give us 98, whatever, 0.20235 over a million. Integer. So I hope that the two of you who are here are convinced that every terminating decimal represents a rational number, right? Not backwards. So not every rational is terminating. I just showed you 1/3. 1/3 is hideous, right? And well, let me show you another number. I'm not going to tell you what. This one is actually rounded up. This is a number similar to 0.33333, but the calculator is less smart than you and I because we have the concept of infinity. This calculator doesn't. It's very precise, very fast, but then it rounds up 77 to 80 at one point. So the calculator will never be convincing, but if we do the long division, 1 divided by 3. Now, this is not going to be division with remainder. This is division with decimals. So 3 goes into 1. No, it doesn't. 0 times 3, 0. We write down, we subtract. I don't want to clutter my paper with that. And subtract. So we have that 1 left. And then we're going to bring down this 0. And we can have as many as we want. And when we bring down the first 0 after the decimal, or the first any digit after the decimal, we put a decimal there. So now the question is 10 divided by 3. 10 divided by 3 is 3, because 3 times 3 is 9. 10 minus 9 is 1. Bring down the 0. 10 divided by 3 is 3. It's very claustrophobic. We're kind of stuck forever in this endless loop. 3 times 3 is 9. Subtract 10. And so on forever and ever and ever. And that's kind of strange. Because what this says is that 1 over 3 is, this here is 3/10. And this here is 3 over 100. And this here is a 3 over 1,000. And we have to go on forever and ever and ever to get to, that's a strange thing. There is notation for this. 1 over 3 is either 0.333, this ... means you got the idea, don't stop. But this is terrible. This is your first argument to favor fractions as opposed to decimals. Decimals often get this, and this is a nice one. Try 1 over 7. That doesn't even look like it's repeating. So that's why you should always go with fractions whenever you have a choice between fractions and decimals. It's very rarely. At the beginning of class, I said 39 over 4. That's nice for a decimal because 4 does not produce these terrible decimals. But the notation that I'm trying to get to is 0.3 with a border. And so here is what we know. Terminating decimal implies, but it's a rational number, but not backwards. 1/3 is a good example that we don't have it backwards. Just because a number is rational, like 1 divided by 3 or 1 divided by 7, that doesn't mean that it's gonna, as a decimal, be terminating. And so every time someone says, I get a decimal, that's really not naming it. It's like, that's a representation. Like 1/2 and 0.5, this is a decimal representation. This is the fraction representation of a number. And if you wanna know whether it's rational or not, you wanna write it as a fraction. So we think of numbers more like in terms of fractions. If you say decimal, that doesn't tell us anything. You have to be more specific. Terminating decimal, and even that, like what's the deal with 1 over 3? And what about 1 over 7? And what about these repeating decimals? What about something like 0.77777? Is this a rational number or not? Well, 0.333 is recognizable. This one isn't. So what I'm going to show you is, here is the fact. If you have a decimal and that terminates, that's rational. If you have a non-terminating decimal, so it goes on forever and ever and ever, if it's repeating, that is still a rational number. So those are the nice decimals, either terminates or repeats. But you can actually kind of put them together. You can clump them together. If a terminating decimal, at the end, you put a repeating 0, 0, 0. Then they're kind of in the same category. So this is a rational number. And what I'm going to show you, what is real fun, is how to prove that. So I'm going to show you how to convert this into a fraction of 2 integers to prove that it's a rational number. Now, one thing is, whenever the languages prove that this number is rational, that means produce a fraction. It doesn't have to be the best one. You're proving existence. There exist 2 fractions. It doesn't have to be nice, and usually it isn't. So here is the algorithm, and that's kind of really cool. We're going to use the number's own badness against itself, and we're also going to exploit strange properties of infinity. Let's call this x. And now That's a very strange equation, I know. Now I'm going to create another equation, and I'm going to put it on the top of the previous one. And we get this other equation by multiplying both sides of this equation by 10. So 10 times x is 10x. And what's going to happen to the decimal 0.7777 when we multiply it by 10? Well, the decimal moves, right? It's going to become 7.77777. The dot, dot, dot is crucial. Otherwise, it's a false statement. If you have a terminating decimal with 5 non-zero digits, it will have 5 non-zero digits after you multiply. We went from 5 to 6, but that's because you have infinitely many, right? There is some strange thing about infinity. And now this is my favorite part. I call it this whole thing, I call it the chop game, because we're going to chop off the infinite tail of the number by a subtraction. We're going to subtract the second line from the first line. Now, 10x minus x is just 9 of them. And now I told you that we're going to use the number's own badness against itself. We cannot say subtract the number from itself because we get 0 equals 0. So we have to do a little manipulation before, but now this is what we get. And now solve for x. How cool is that? This is the division I didn't want to show you at the beginning. So the last 8 is because of rounding. It takes 77, it rounds up to 80. All right, any questions? So let me write down this statement as well. So if a non-terminating decimal, and you understand non-terminating, there is no last digit, there is always another one. If a non-terminating decimal is repeating, then it too represents a rational number. Now, the repeating block could be, you have to be very careful to understand the difference between these two. You see the repeating block, this is 0.25555, and this is 0.25252525. So you overline the repeating block. We're going to do both. But I first want to do the 0.25. So infinity is kind of touchy. So if we write 0.252525 equals x, and we multiply it by 10, then what we're going to get is 25252. That is actually, wait. That is actually not allowed. You see, that subtraction, if you multiply it by 10, that's not good. Because imagine that you're copying down this number twice, and then you shift one of them. A shift by 1 unit is going to put a 5 over a 2. That subtraction is not allowed. The only way you chop off the infinite tail if there is a 2 over a 2 and a 5 over a 5. It's not hard. Basically, if you think about just a fixed digit, when you multiply it by 10, it's going to go here. We have to multiply it by 100 to move it there. That's all. So we're going to start with 0.25252525, and that's our strange equation if you call that x. And then instead of 10, we're going to multiply both sides by 100, and you should not fake it. Make sure you're going to need to actually see who is over who. So we're going to get, so what I do, the next step, we're going to subtract. And for subtraction, the decimal point should be aligned. So I'm going to put the decimal point there. I'm going to use my finger. That is the if we multiply this number by 100, we're going to get 25.252525, and I copy that number around the decimal point. And this thing, this infinitely long decimal subtraction is only allowed if you just kill the whole thing. So that means a 2 has to be over a 2, a 5 has to be over a 5. And now when we subtract, we get 25 on the left-hand side and 99x on the right-hand side. Right? And now solve for x. 25 over 99. I was thinking about rounding, but it depends, I think, where it stops. So 25 is being rounded up to 30. 52 would be rounded down to 50. But 25 was rounded up to 30. You see? Okay. Any questions? Fun stuff, huh? So let me show you sort of the worst case scenario. Okay. Ugh. No, I don't want to do this one. Okay, so here's the number 0.52832. This is going to be a rational number. So it's, if it starts, you know, this is a finite beginning. It doesn't, so the repetition doesn't have to kick in all at once, but once it kicked in, it has to stay. So there has to be an infinite repeating block that it ends with. But before that, all kinds of things can happen. And so there is going to be two stages here. And the first stage is the more important one, where you want to kill off the repeating block. That's the most important one. Then after subtraction, we get the terminating decimal. That's a very easy fix. You have seen it. It's just a matter of multiplying upstairs and downstairs by 10 powers. So if you look at the repeating block, this thing is 52832323232. So when you multiply this by a 10 power, you want a 2 to be promoted, not here, but here. So again, 100 will do. It's basically how many digits long is your repeating block? That's how many zeros you need after a 1. So a 3-digit repeating block means you multiply by 1,000. A 7-digit repeating block, means you put 7 zeros after the 1, and that's going to be the multiplication. So we're just going to multiply by 100. And again, I told you, don't just fake it. So when we multiply by 100, we get 52.83232323232. And it doesn't matter what's at the end. And I found that mysterious or magical. And then I realized, just look at it from the point of view of a single decimal. 2 over 10,000 has to be promoted. When you multiply it by 100, it's going to be 2 over 100. So it will always work. But you have to align, because you have to find a point where it's the same, it's the same, it's the same, especially if you want to use the calculator. This is your subtraction with the calculator. You see what I did? So you have to, don't just pick it, it has to be truly aligned. So for you to see 52, I'll do it with hand, but I'm not good at it. So 99x is the right-hand side, and then, especially not out loud, okay, this wasn't so hard. There was not much borrowing or whatnot. But I'm going to do it just to be careful. 52, oops, I already did 52.832 divided, minus 0.528. All right, so we're good. Again, don't worry about this terminating decimal. If the infinite tail is gone, we're in good shape, because now we're just going to multiply both sides by another 10 power. How about 1,000? right? So now we want both sides to be integers, because remember, we want to prove that this hideous thing can be written as an integer divided by another integer. So we're going to multiply both sides by 1,000 now, because if we want the decimal to migrate to the end, and then don't forget to multiply the other side. And then remember, I told you, you don't have to worry about simplifying. This could take an afternoon. No one really cares. Yeah, they're both divisible by 2, but remember, the goal was prove that it's rational. Well, the numerator is an integer, the denominator is an integer, done. Well, let's see if it works. 52,304 divided by 99,000. All right. Any questions? You want to see one with 3-digit repeating block? I'll just put it in the homework and you ask me next week. This is a really cool skill. It's actually is in pre-algebra, because in pre-algebra we learn to convert between decimals and fractions, but I doubt if it is still being taught there. But then from then on, we pretend that you guys know it, which is not a very nice thing to do. Okay. All right. So we'll do a 3-digit long. So let's say 35.17204204204. So just look at the repeating block. Don't worry about anything else. The repeating block, basically after multiplication, you want this 2 to be promoted to sit here. And that means you migrated by 3-digit. That means 3 decimal places. That means 1,000. And so 1,000x. And after subtraction, we're going to have 999 of them. And let's see. So I'm going to start with the decimal. And then with, so it's going to be 35,172. 35,172.04, and then 204, 204, 204. And magically, it will work. Works means that you have perfect alignment, that a 4 is over a 4, a 2 is over a. Otherwise, this subtraction may not be allowed. Infinity is kind of touchy. And now, this is the decimal subtraction here. You see, when they are equal, that's 0, 0, 0. So this is what you want to write into your calculator or with the paper. I know you guys are pretty good with paper, actually. 35,172.04 minus 35.17. And that's 35,136.87. And that's 999x. We fix the infinite tail. We got the terminating decimal. That's an easy fix. We want the decimal to move 2 decimal places. So we're going to multiply both sides by 100. So that's 35,13687 equals to 999 and 2 zeros, many x. And now both sides are integers. Solve for x. 35,13687 divided by 999.03. 35,13687 divided by 999.00. There it is, 35.172042042. So it always works. Always, always, always. Okay. So here is what we have. Here is the decimal. And here is the nature of the number. There is not if there is a noun like the classification of whether it's a prime or a prime, rational or irrational, I don't know the word for that. So if the decimal terminates, the number is rational. We don't have it backwards. If the decimal doesn't terminate but repeats, so I'm going to call it repeating non-terminating. Although repeating kind of says it, terminating. That too means that the number is rational. Now, just to manage time, I'm not going to prove it to you today that square root of 2 is irrational, but we might spend Wednesday with that. It's not that hard. You can get it. This is an algebra one. So, but now let's just accept by authority until Wednesday that square root of 2 is irrational. And let us also agree that we don't have anything backwards. So what if a number is rational? It's a fraction of two integers. As a decimal, is it always terminates or repeating? We don't have that fact. We just have that if you start with a nice decimal, that's rational. Now, question. So here is square root of 2. We just accept that this is an irrational number. And then the question is, how can we write square root of 2 differently? Can we write it as a fraction of integers? If we could write square root of 2 as a fraction of two integers, that would make it rational. That's the definition of rational, right? Square root of 2 is not a fraction in the sense, yeah, you can write square root of 2 over 1, but you're not going to write it as a fraction of two integers. We just accept this fact today. And just think about it. If you're given an irrational number and you have to prove that it's irrational, that's a much harder problem because it's not a matter of, well, just produce an example. Instead, you have to defeat infinitely many possible attempts, right? You have to say, no matter how you try, it's not going to work if you say, I tried to write square root of 2 as a fraction of two integers. I tried for 2 hours and I couldn't do it. That doesn't mean it's irrational. That might mean, you just needed 5 more minutes. So this is what I've referred to, that proving that a number is rational is much easier than proving that it is irrational. It's going to take some skills. But no, the answer is no. Irrational, that's what it means to be irrational, right? Square root of 2 is irrational. And irrational numbers, the definition is you cannot write it as a quotient of two integers. Can do it, can do it, cannot do it. Okay, well, maybe as a decimal, right? These are the two representations, fraction and decimal. Now, the calculator, you can enter square root of 2, but that doesn't tell you anything. Square root of 2, or we can say it's a long decimal, but it could be long and terminating or long and repeating or nothing. So the calculator does not tell us anything. Can it repeat? Or can it terminate? So if we write down square root of 2 as a decimal, can it terminate? And the answer is no. For the same reason, because terminating decimals always represent rational numbers, and we agreed for today, we're going to believe that square root of 2 is not rational. Can it repeat? No, because that too makes it rational. So what is left for square root of 2? So there is going to be this thing called exact value and approximation, or approximate value. And if you hear, and you will hear, this is going to be the rule, that we want exact value. The only way we can write square root of 2 as an exact value is if you write it down. It's the number that when you square, you get 2. Now, any approximation, because I'm sorry, I forgot to say, what kind of a decimal presentation is left for square root of 2? It's terrible. It's non-terminating, non-repeating. Right? Because terminating means rational. Square root of 2 is not rational. Repeating also means rational. Square root of 2 is not rational. So what is left for square root of 2? Basically, terrible. It's non-terminating, non-repeating. You can have all kinds of other patterns, just not infinitely many repeating blocks. For example, here is a famous irrational number. Well, we're going to generate it by decimal by decimal. And basically, the rules are going to be don't stop, make sure you don't stop, make sure you don't repeat. So I said 1, 0, and then I'm going to say 1 again. And in order to avoid repetition, I'm going to put in there 2 zeros and a 1. And in order to avoid repetition, I'm going to put there 3 zeros and then 4 zeros and so on. So that's an irrational number. And if you keep the zeros, these digits could be anything. And so for a rational number, you have all kinds of choices, but then you either terminate 0, 0, 0, or you have no more choices because you're repeating, and you can go on and still have all kinds of choices when you're generating an irrational number. This should kind of give you the first feeling that, yeah, there are more irrational, that it's reasonable that there should be more irrational numbers than rational numbers. Because after a while, if you're writing a rational number as a decimal, after a while, you have no choices then. Either you're done, repeat 0, or repeat the repeating block. Meanwhile, you have all kinds of choices left for an irrational number. But we cannot really write down square root of 2 as a decimal or as a fraction. So we're going to write it like square root of 2. And anything you try, like 1.414, this is a rational number. Why? Because it's a terminating decimal. This is not square root of 2. This is just approximation. Indeed, if we take 1.414 and we square it, okay, it's close, but not quite. And it doesn't matter how long you go copying the digits of square root of 2, because guess what? As long as you write a terminating decimal, that cannot be your irrational number, because terminating decimals represent rational numbers. So here we have our finite lives, our finite sheet of paper, finite graphite. If we started to write square root of 2 as a decimal and we want the exact value, we could sit there and write digits till the end of times and we would still not be done writing down a single number. That's kind of, I don't know, that was a shock to my system, this whole irrational numbers business. I thought numbers were all nice and the rational numbers filled up the number line. These are just, you know what, these are better and better approximations. None of them is the exact value. You can grab any one of them and you square it. It's always going to be a little bit less because there is more decimals added. So we're under 1.41421 squared. Close, but no cigar. In fact, your calculator is pretty smart. Mine, if it was close enough, it rounded up to 2, and then I have to subtract 2 and multiply it by a gigantic 10 power to get that. This calculator will remember. Never mind. Don't worry about what I just said. No, here is what I did. So I grew up with much simpler calculators than you do. And mine knew less than this one. But if you say square root of 2, my calculator did this. And then if you squared it back, my calculator showed this. But already was off by a little bit because instead of square root of 2, it just remembered a long terminating decimal. You squared it back, it was below 2. But it showed 2 because the rounding made it so. And then if I subtracted 2, my calculator said 0. But if I multiply that, but there is a tiny, tiny difference. It's 0.000 or somewhere. So if I multiplied it by 10 million or something like that, that was a non-zero number that I got. This one is smart. This one knows, it's kind of remembers symbolically. And this is what it is symbolically. We cannot really, they're slippery. Irrational numbers is not something we can truly understand or possess. Not as a fraction, not as a decimal. What is it? It's a number that we can approximate, and it's the number that if we square, we get 2. That's square root of 2. Actually, there are 2 numbers that square to 2. One of them is square root of 2. The other one is the opposite of that. So what is square root of 2? It is the positive number. X such that x squared is 2. And you know, this looks strange, but if you think about something like 3/7, that tells you too, well, it's a number you get when you divide 3 by 7. Sort of driving instructions and not approximately this much, right? 3/7, you don't, it's how you get that number. So it's the same. Well, it's a number that if you square, you would get 2. And so square root of 0 is 0. Why? Because 0 squared is 0. Square root of 1 is 1. Square root of 2 is irrational. Square root of 3 will be irrational as well. Square root of 4 is nice again. That's just 2. Square root of 5 is irrational again. But until now, all these irrational numbers had primes under. 2, 3, and 5 are primes. So what about square root of 6? And maybe there are numbers, square root of 7, square root of 8, square root of 9 is nice again, we know. But so here is the question. Is there a middle ground? Is there anything in between? It's as bad as irrational, or it's a perfect integer. Can we get a rational number, but not an integer, a fraction? And the answer is no. If it's not an integer, then it's as bad as it gets. So if under the radical sign, the number sitting is not a perfect square, then it's irrational. It doesn't matter whether it's a prime number or a composite. If it's not a square, it's going to be all irrational. And a big part of, one of the most beautiful part of intermediate algebra is now we have, instead of numbers and letters, we have nice numbers, yucky numbers, and letters. So there's going to be 3 groups or worse. But basically, we're going to revisit algebra where we have these nasty things like square root of 2 walking around, because any other way we try to write square root of 2 as any other way we try to write square root of 2, we're going to lose precision. So if we want to compute using exact values, and guess what we do, we're going to have to carry these symbolic things like square root of 2. And that's interesting, actually. Operating with those radicals, that's interesting. Thank you, guys, and we'll pick it up here on Wednesday, and we'll prove that square root of 2 is irrational.